of my talk. Yeah, so this is the work between my group and Professor Miyala Sensei group on MgV2. And this work specifically on the co-addition of dysprosium and lanthanum oxide rare earth on enhancing the critical current density of MgV2. Just a little bit of introductions. MgV2 it has surprisingly high TC of about 39 Kelvin. Consider that this is a non-oxide based superconductors. There are a few advantages of why we choose MgV2 as the material to enhance the critical current density. The crystal structure is very simple. It's a binary compound. The coherent length is larger if you compare to copper oxide-based superconductors. And also, this material, it has got the weak link free behavior at the grain boundary. Again, if you compare to high TC superconductors, this is definitely one of the great advantages. Starting materials are light, especially boron. And if you look at magnesium, it is actually not a very expensive material. And because of the slightly higher TC of about 39 Kelvin, then we can make use of a refrigerator or cryocooler or even liquid hydrogen of the boiling point of about 20 Kelvin to cool this material. There are a wide range of superconductors. For example, on the left-hand side, we have like wires. These are one of those very useful high-temperature superconducting wires. Here, if we compare the size of a superconducting wire and to the normal copper wire, the size is actually a lot smaller. And also, you look at the DC cable applications. So right now, actually, there are such products in the market already. So that's why MgV2 it has got the potential to be applied into one of those applications. And we know that there are two techniques to prepare about MgV2, like it was mentioned by Professor Jack and also Professor Oka Sensei. We have two techniques to prepare. The first one, which is the in situ technique, whereby reactions take place between magnesium and boron. And compared to the other technique, which is ex situ, whereby we make use of pre-reacted MgV2 powders, or we can make use of the commercial MgV2 powders. The advantages of making use of the ex situ, if you can optimize the heat treatment conditions, then the density can be increased. If we can increase the density, then the packing factor can be increased greatly. However, the disadvantages of ex situ technique over the in situ is that the ex situ technique rely on relatively higher sintering temperature. That's because what you need is sintering to connect those pre-reacted MgV2 grains. Let's look at the motivation for this work. There are several reasons why we choose dysprosium oxide and also lanthanum oxide. First of all, we know that the two dopants, they do not substitute into the lattice structure of MgV2. If that is the case, then the dopant does not decrease the TC. For example, here for dysprosium oxide addition of about 5-8%, there's only a reduction of TC by about 0.5 Kelvin. Same thing as reported for lanthanum oxide, the reduction of TC is also very small, less than 1 Kelvin, with about 5-8% of addition. The second reason is that we also noticed, as what reported previously, the grain size of MgV2 was refined either by addition of dysprosium or lanthanum oxide. If the grain size is reduced, that also implies that you have more grain boundary for pinning. And the third reason is that if we make use of the two dopants for reaction with Mg and B, you have those byproducts or the impurities form, and in turn, those impurities can act as effective pinning center. Let me talk to you about how we prepare samples. Starting materials is magnesium, and then we use carbon encapsulated boron powders. So it has got about 1.35% of carbon in the boron powder, and then the rest of the powders are lanthanum oxide and also dysprosium oxide. So meaning that in those samples, you expect to have carbon substitutions. Is a very simple solid state reaction method whereby you mix those chemicals together, and the dopant, the ratio of the dopant that we use is actually from 0.25 to 1 weight percent. So meaning that the maximum weight percent of the dopants that we use is only 1 weight percent. Again, the idea here is that we try to minimize the use of those chemicals to reduce costs. After mixing, what we do next is to press those powder into pellets, and then we wrap those pellets with titanium foil, hoping that to minimize oxidation, and then those pellets were subjected for sintering in argon gas flow at 775 degrees Celsius for 3 hours. Characterizations, I'm going to show you the result that we obtained from X-ray diffraction, scanning electron microscopy, and also from the squid measurement. The XRD patterns show that we have formation of some impurities, especially if you look at the peak here. So that is actually you have unreacted lanthanum oxide, you have also unreacted dysprosium oxide, and also you have dysprosium lanthanum phase. However, when we calculate the intensity of those impurity peaks, we notice that their intensity is actually quite low compared to the intensity of Mg2 peaks, indicating that the amount of those impurities, they may not be that great. Here, this is the table that we calculate. For example, here, the volume fraction, we have Gb2, MgO here, that's the unreacted dysprosium oxide, and that is the unreacted lanthanum oxide, and this is the dysprosium lanthanum phase. The lanthanum, dysprosium lanthanum phase only appear for high amount of addition level. So the rest of the byproducts or the unreacted products are from here, dysprosium oxide and also lanthanum oxide. And we also noticed that the MgB2 phase actually decreases slightly. And that is also due to the fact that you have the increase of other impurities or unreacted products. As what we expected on this column here, lattice parameters, the lattice parameter of A and C axis did not change much. Because of that, we also expect that the TC would not change much. So I will show you later about the result of TC. This is the SEM images, basically just right to highlight that, and we know for in situ samples, porosity is great, and all the samples, they have the density about less than 50% of the theoretical density. This is the backscatter SEM images. Basically, what we would like to highlight here are those white color dots. those white colored dots correspond to mainly the unreacted lanthanum oxide and also dysprosium oxide. Just want to show that those particles they are distributed over the sample. This is the high magnification SEM images. The purpose for us to capture those images is actually for us to calculate the grain size, which I'm going to show you in this table here. Crystalline size we calculate by using the Shearer equation. So that is the average grain size that we calculated based on the SEM images. The average grain size decreased according to the co-addition amount of the dopants as what we expected, because as what we reported previously, dysprosium oxide or the lanthanum oxide alone addition into MgP2 decreased the grain size. So this is actually consistent with previous result. And the crystalline size also decreased slightly in such a way that it decreases with the increase of the co-addition amount. The main thing, the main measurement for this work is actually about JC. We noticed that the selfie JC has been increased a lot with the co-addition of dysprosium and lanthanum oxide, especially for 1 weight percent co-addition level, reaching about the value of more than 430 kilometer m per centimeter square. Not only that, we also noticed that JC at applied field, say here around 1 Tesla, 2 Tesla, also increased in those samples with co-additions of dopant. In order to assess the pinning, what kind of pinning mechanism in the sample, we plot the so-called flux pinning force, the plot over the reduced applied field. And the peak here, this peak here, the value is about 0.2. And if you look at the pinning mechanism, the value of 0.2 for that peak value actually correspond to the grain boundary pinning as the dominant pinning mechanism in the sample. And this is actually consistent with the result of the decrease of average grain size of our sample. Here, that is the TC plot. As what I mentioned just now, the TC did not decrease much, about 0.5 Kelvin, as what we expected. And the JC at cell field as well as applied field also increased compared to the pure samples. As a conclusions, we show that very small amount of co-addition for dysprosium oxide and lanthanum oxide in the MgP2 can actually increase the flux pinning and also JC of the sample. The highest selfie JC that we obtain is about 433 kilo m per centimeter square. That is achieved in the 1 weight percent co-addition level sample. So the cell field, the increase in selfie JC is actually attributed to the improved grain connectivity. However, when we plot the flux pinning versus reduced field, we notice that actually the field dependence of JC increased. That is because due to the grain boundary pinning. So again, this is consistent with the decrease of average grain size of the sample with the co-addition level of those dopant. So we show that so this is actually the JC can be increased greatly by using a very small amount of co-addition dysprosium oxide and lanthanum oxide. So finally, I would like to acknowledge financial support from SIT under the exchange program, and also the Ministry of Education Malaysia, and also University of Putra Malaysia. Thank you. This is just to show you that where is University of Putra Malaysia. It is not very far from Kuala Lumpur. in the near future, if there is no more restriction for travel, if you happen to come to Malaysia, yeah, please visit us at UPM. Thank you.
Okay, thank you, Sensei. Thank you very much for your wonderful presentation. This paper is open for any comment or correction.
Yeah, I have a question.
Please.
Yeah, thank you for Professor Chen for this nice talk. I would just like to know why the ground boundary or the crystallite size decrease when you increase the percentage of dopant.
Oh, see here, yeah.
Yes, please.
Yes, yeah. Okay, Professor Jack, this is what we believe because previously, as what previously reported, what they found, the grain size was decreased by dysprosium or also by lanthanum oxide addition, is because those dopant they segregate within the grain, outside the grain, sorry. So by having those distribution of the dopants, they actually prevent or they reduce the growth of the grain. So this is according what it was found previously. So in our case, we also believe that the same thing happened.
And do you think if you increase the density of your samples, you can increase the grain boundary pinning in order to improve again the JC?
Yes, yeah. Yes, I believe so. Yeah. Yes.
Yeah.
Okay. Thank you.
Yeah. Okay. Thank you.
Thank you. Any other question or comment? So if there is no questions, I would like to thank all three speakers for the excellent contributions. So we will close the session, and next session will be start on a 15:35 after the small 10 minutes break. This is like all young investigator forum. The students like postdocs and doctoral students and master students will be present. So we will be come back again like 15:35. So thank you very much for all. Let's see. I will close this session here.